So, hello everyone. This presentation is the second part focusing on shape deformation. And last time we've seen an introduction to volume-based deformer from parametrization. And now we are going to see other type of approaches, such as the freeform deformation, and its more recent improvement that are the cage-based deformation. And finally, we will finish with a few words on vector field-based deformation. And we start with freeform deformation, also called in short FFD. So this deformation, they can be understood also as grid-based deformation. And the idea is the following. So we have an arbitrary shape which is placed within a rectangular or Cartesian grid that we call a lattice. Then at interactive time, we deform the grid, and this induces a deformation of the space inside the grid that can be computed using some smooth function, and this special deformation is applied to each vertex of the shape. So this method is commonly used to apply local deformation or warping on 3D shape and 2D images. You can see an example of its use in a professional 2D software. It's also one of the common methods used to deform medical images for retargeting purpose, for instance. So the question is, can we compute this special deformation based on the grid modification? And actually, the idea is to use the standard smooth approximation function. Note that in this case, I will use approximation with respect to the grid and not necessarily interpolation as we saw for keyframes. As we are using a Cartesian grid, we can use the standard Bézier or B-spline or NURBS functions. So I do a short reminder with Bézier. Usually Bézier are explained to define a 1D curve C approximating n points pi, which is called a control polygon. C of u is the sum over all the a between 0 and n of some basis function bi of u times pi. So bi of u is the basis function using the Bernstein polynomials in the case of Bézier. And so the Bernstein polynomials, they are the NCI u to the power of I, 1 minus u to the power of n minus I. And NCI are the binomial coefficient of A among n choice. So this function C of u can also be understood as the 1D deformation of the unit straight segment between 0 and 1 into C. When we increase of dimension, we can define a 2D surface S approximating some points Pij, and the Pij must be organized as a grid this time. And this time, the surface S has two parameters, u and v, and is S of u and v given by the sum over A of sum over j of pi of u, bj of v, pij. And the new basis function are actually the product of the 1D polynomials, and this procedure is also called tensor product in this case. And this is a generic way to go from one dimension to a greater one. So similarly to the 1D case, now the function S of u and v can also be understood as a 2D deformation of the unit square between 0 and 1 squared into S. So now, following the same approach, we can actually extend it to a 3D volume V, approximating points on the lattice P, I, J, K. And V, depending of U, V, and W, is given by the sum over A, sum over J, sum over K of Bi of U, Bj of V, Bk of W times Pijk. And this function V is actually a 3D deformation of the unit grid between 0 and 1 cube into V. And we can use this function as our volume deformation. In this case, the Pijk are the position of the deformed lattice, and the parameters u, v, and w are the local coordinates of the shape within the lattice. And so this is the approach of the FFD, which is one of your exercise of the lab class. So we suppose that we have as input the position of the grid, G of AJK, and then you have a mesh inside this grid. So the initial coordinate of the mesh, we call them P of M, and they are given by the coordinate xm, ym, zm, all between 0 and 1 with respect to the grid. Then the deformation of the vertex M is given by Q of M, given by the sum over A, sum over J, sum over K of Bi xm, Bj of ym, and Bk of zm, times the grid position J of AJK. One thing we can note is that for each vertex, the formula involves a triple loop over the grid position, which involves the evaluation of the Bernstein polynomials, which can be computationally expensive. But actually, if you look, the result of the product of the basis function Bi times Bj times Bk is actually independent of the grid position and only depends on the initial vertex coordinates. So this part can actually be pre-computed to avoid having to evaluate it at runtime. And at the end, the actual evaluation can be seen as Q of M to be given by the sum over ijk of the weights depending of ijk and M, and the grid position J of ijk. And you can see the type of deformation applied to the shape when the grid is modified. Using smooth approximating polynomials ensure that your final deformation remains smooth as well. And of course, we show the case where B are the Bernstein polynomials in the case of Bézier function, but you can take any basis function instead, such as the B-splines or NURBS. So this approach of FFD was actually one of the first spatial deformation introduced in 1986, initially used with Bézier. One of the interests is that it can be applied to any shape embedded in the grid in a unified way. It can be points, curves, surfaces, or volume. Everything is deformed uniformly. Using FFD is, however, associated to some limitation. First, if you want lots of degrees of freedom for the details, you need a grid with more samples. And actually, using large grid is very hard to manipulate in 3D. Also, the second limitation is that this grid deformation is not aware of the morphology of the shape. For instance, in this case, imagine it to be like a mouth of some animal, we may want to modify the upper part of the shape, like moving it up, without moving its bottom part. But it's hard to achieve in freeform deformation, as the deformation propagates in all directions based on the grid. Otherwise, we would need a much more finer grid, which would be more costly and hard to handle. So it came more recently the idea of using a different approach that still allows smooth spatial deformation, but can better take into account the morphology of the shape. The idea is to use a cage surrounding the shape. This cage doesn't have to be a rectangle. It can adapt locally to the morphology or topology of the shape we want to deform. And the use of a 3D cage for mesh deformation was introduced in 2005. But how can we compute this spatial deformation from an arbitrary cage surrounding a shape? So first we can inspire from the notion of barycentric coordinates. So barycentric coordinates are a way to generate a relation between any point P inside a triangle with respect to its position toward the triangle vertices P1, P2, and P3. For such triangle, we call the barycentric coordinates lambda 1, lambda 2, lambda 3, and then for any point P in the triangle, P1, P2, P3, we can write P equals lambda 1 times P1 plus lambda 2 times P2 plus lambda 3 times P3. With lambda 1 plus lambda 2 plus lambda 3 is equals to 1, and all lambdas are between 0 and 1. These lambdas, they can be computed from the relative area of the small triangles shown in the figure with respect to the total area of the triangle. So we remind that the area of a triangle can be computed from the norm of the cross product between its edges. And this formula works for a 2D triangle, but it can also be generalized to tetrahedron in 3D or any simplex. Now, in the cage deformation, the idea is to generalize this notion of barycentric coordinates to a shape with more vertices. And we will still try to look for a formulation with p is equals to the sum over all the points, lambda I times pi, or in other form, sum over I of omega I pi divided by the sum over I of the omega i's, where the omega are some linear coefficients that are applied to the vertex position, and they can be normalized afterwards. And now in the next part, we show some method that can be used to compute these weights omega I. So a first approach to define these weights is the use of the Weierstrass coordinates. So the Weierstrass coordinates are a generalization of the use of relative areas, where omega I is equals to the area A plus 1 plus area A minus area BI divided by the area A plus 1 times the area I. Or we can also express it using the angles of the triangles, or more precisely, the cotangent of these angles. So the Weierstrass coordinates were the first generalization of barycentric one, proposed in 1975. So they have still good properties in the nice cases, but actually they would only work in 2D and for convex polynomials. Otherwise, we may have negative weights or even poles appearing. So they are not so much used actually in graphics. So a much more commonly used approach is the use of the mean values. In 2D, the mean value coordinates can be expressed as follows. So we've got omega I to be equals to tangent alpha I minus 1 divided by 2 plus tangent alpha I divided by 2, and these tangents are divided by the norm between pi and p. And we are going to see in the next slides from where this expression comes from. These coordinates were proposed in 2003 in the 2D case, and their generalization to 3D was proposed in 2005 by two different groups in parallel, actually. And let us now look at the explanation of this formulation. So we consider an arbitrary boundary curve B parameterized by theta, which is the angle in which this point is viewed from a position P inside this curve. In other words, we project the value of the curve on a unit circle surrounding the point P. This curve has a value f of theta for each theta. And then we look at the average value associated to the point P, where we weight each contribution by the inverse of the distance between P and the point of the border. So the average value is f hat to be equals to the integral over the entire circle of this inverse distance function times f of theta and divided by the integral of the inverse distance for the normalization. So now in the case of cages, we don't have continuous curves, but actually piecewise linear boundaries. And in this case, the integral can be split on each edge. And each edge is the integral between some theta 1 and theta 2 of the inverse distance times f of theta. And in conducting actually the integral on a straight segment, we could actually end up with the result being f of pi divided by the norm between pi and p plus f of pi plus 1 divided by the distance between pi plus 1 and p and multiplied by the tangent over theta 2 minus theta 1 divided by 2. And so we can also reorganize all these terms as being coefficient omega I multiplied by f of pi, where f of pi is actually the coordinate of pi itself in our case. And then we have this weight omega I for a given pi, if we conduct all the formula, given as tangent alpha I minus 1 divided by 2 plus tangent alpha I divided by 2 divided by the distance between pi and p, as there is the contribution from the two segments passing by pi. And then we end up in the formulation that we saw in the 2D case. So in the 3D case, the idea is actually similar, but in this case, we have to project the 3D cage on a sphere surrounding the vertex. So the computation is a little bit more complex, so I won't go into the details, but you have the algorithm from the original publication. And the formula is expressed in function of the normals and angles on the side of the tetrahedron made in projecting the cage, the triangle of the cage, into a sphere, and then extruding this triangle to pass by the point P. And here are some examples of the use of mean value coordinates. They can be used to generalize barycentric coordinates in 2D. They can also be used to define some local coordinates based on the boundary of the mesh, and one application of that is to build a 3D texture from a surface boundary. And of course, they can be used to model 3D deformation from a sparse cage. The cage allows to have few degrees of freedom compared to the mesh inside it, and compared to the grid-based approach, the cage can actually surround the limbs of the character, so when deforming one limb, it doesn't impact the other one. Actually, mean value coordinates are not the only possible one. There has been some other propositions, such as the use of harmonic coordinates in 2007 by a group at Pixar, notably to involve the deformation of the character when working on the movie Ratatouille. And in this case, the weight omega is computed from the harmonic equation with values only initialized on the vertices. The good part of these harmonic coordinates is that they are always positive, even from strongly concave cages. However, there is no closed form solution. Finding the weights needs therefore the use of numerical solver. And here is an example between the harmonic coordinates and the mean value coordinates. One of the main issues with the mean value is that the weights associated to concave regions propagates outside the cage, and then they interfere when moving a limb with a closer one. In the case of the harmonic coordinate, such weights do not propagate, and it allows to separate the legs without artifacts. Actually, harmonic coordinates are only one improvement over the class of generalized barycentric coordinates. There has been also the green coordinates, providing a closed form solution for the harmonic kind of coordinates. The biharmonic coordinates that even further improves the smoothness of the deformation. There has also been work toward the use of multiple coordinates for a single character, and it's called multi-cage, or the generalization of the use of mean values to quad meshes for the cage instead of triangular ones. Also, I didn't talk about it, but the creation of a good cage surrounding the shape is not always an easy task to do manually, so we can also find several works trying to generate such cages automatically. And now we end with a specific type of spatial deformations. Deformation that can be represented as streamlines along vector fields, or in other words, shapes that are advected along velocity u in time. So we define the vector field, or the velocity u, as the function of coordinate ux, uy, uz at position x, y, z. And at an arbitrary time, we have the time derivative associated to a position given by the velocity field applied to this position. And the deformation can be characterized as the integration of the vertex position along the streamline. So the new position p1 is equals to p0 plus the integral over the time t of the velocity u of p of t dt. Another definition we can give is that at time t, the instantaneous deformation at position p is f of p and t is equals to p plus the velocity u of p and t. Or in other words, f is the identity plus u. One of the nice things with vector field is that it allows to easily model deformation that do not self-intersect, which is always true for smooth vector field with a norm of the velocity different of 0 or doesn't go to infinity, as the streamlines of the fields do not intersect together. The main limitation of the use of vector fields is that they can be hard to define and control actually. We can, however, note that for all physical-based deformation, basically they can actually be seen as vector field deformation, and in this case the field is defined from the laws of physics. Among all types of vector fields, the use of divergence-free vector field has several advantages. We remind that the divergence of a field u can be written as nabla.u, and it's the sum of the partial derivative of the coordinate of u along x, y, and z. And it's actually a measure of the local gain or loss of flow passing through a position. We say that a field is divergence-free or is a solenoidal field if its divergence is zero everywhere. For instance, magnetic fields or incompressible fluid velocity are divergence-free. And one of the main interests of these fields is that they are volume-preserving. Here it's a short demonstration in 2D. We saw that the deformation function f can be written as identity plus the velocity. So the Jacobian matrix G of f can be written as follows. Now we also saw that deformation preserves the volume if the determinant of the Jacobian matrix is equals to 1. Then expanding the determinant of the Jacobian matrix expressed with the velocity leads to the cancellation of several terms, and we actually end up with the equation of the divergence free. In the case of interactive deformation, we have to build efficiently divergence-free vector fields. And one way to build such field is to consider two scalar fields, A and B, and to construct U as the cross product between their gradients, nabla A cross nabla B. And it's actually easy to see that these products generate a divergence-free vector field in expanding the divergence of the cross product and noting that the curl of a gradient field is 0. This type of approach has already been proposed first in 2006 to generate interactive deformation of local pulling and bending along user gestures that are volume preserving at every point and are free of self-intersection. Note that these tools are still new on the research side and they are not yet well integrated into the standard 3D modelers. And in this example, the fields A and B are localized in considering they act in a radius r and then smoothly decrease towards 0 around it. Then a translation motion is defined by a constant vector field in the inner region, and it can be defined as the dot product between some vector u and v that are orthogonal together and with the translation direction, and p minus p0 with p0 being the center of the rotation. And similarly, a bending can be defined with a linear and quadratic field, with A being the bending axis. And this is some result of such approach, which is able to push and pull material like a piece of clay while ensuring that the deformation is volume preserving and free of self-intersection. One of the limitations of the approach is the computational time required by integrating the vertices along the streamline of the vector field, which is more costly than applying a closed-form parametric deformation directly. Finally, and like similarly to the case of parametric deformation, we can wonder if we can apply vector field deformation to an implicit surface and how. So we consider an implicit surface to be defined by the ISO value of a function j, and we consider a velocity field u. Then the implicit surface S prime advected by the velocity u can be computed by the zero ISO value of a time-evolving j function. And the equation of evolution of j is actually this partial differential equation, the partial derivative of j with respect to t, plus the dot product between u and the gradient of j is equals to 0. And one thing we can note is that only the normal component of the surface changes the shape, which is expressed by the relation dot u with the gradient of g. And remember that for an implicit surface, the gradient of g is actually the normal of the surface for g equals 0. So for instance, a field of rotation applied to a spherical surface will have a 0 component. The surface is just not changed at all. And a translation applied to a sphere will have some non-trivial component of deformation, as you can see in the figure.